Good morning, everybody. It's an absolute delight to have Professor Elisabeth Guazzelli here at ICTS, and it's a great pleasure to introduce her. So she is a CNRS Research Director at the, and I'm going to read this out, Laboratoire Métier et Système Complex.
Yes.
At the Université Paris-Cité. So most people here know her as the editor of JFM Rapids, right? She's the one in charge of JFM Rapids. So, of course, her work on suspensions and granular flows and among many other things is legendary. And we know that her book and her review papers are very popular. So here is her book, which is in our library. And I'm going to request Babette to sign it.
Oh, thank you. I will.
So does somebody have a pen? Yes, Rajeshi.
Okay. Should I sign with the full signature of Babette?
Whatever you like.
Okay.
I think the full signature and Babette is good.
Okay.
Because that way everybody will know it's you. Thank you. So that's an autographed book for our library now. And so, yeah, one thing is she asks these very fundamental, deep questions and answers them by means of brilliant experiments, and she supports it by very nice theory. So, of course, this immense contribution or immense effect on this field has to be rewarded, and it's been recognized by so many things. And remarkably, she's won both the Euromech Fluid Mech Prize and the APS Fluid Dynamics Prize. She's the latest winner. So it's really, really an honor to have you here. So over to Babette.
Okay, thank you very much, Rama. And thank you for inviting me to come here. It's a beautiful place, first time. As you may know, I'm for 3 months here, visiting the Indian Institute of Science and visiting Prabhunath, and I'll be happy to discuss with you anytime. And it's a delight to be here. So I will talk of something I thought that this problem of falling particle in vortical flow will interest you, and I think we discussed already this morning some of this issue. And this is a work that we did in Marseille. So I was for a long time in Marseille. I'm still a little bit in Marseille and a little bit in Paris. I am in between. It's only 800 kilometers, and you can travel by train, the fast train, which is 3 hours, the TGV, if you've taken it. Anyway, so this is something that I did with my colleague Laurence Bergugnou, and we have been working with Laurence a lot on that, and with Gilles Boucher. Diego Lopez, I mentioned him, and we did also things with fibers with Diego, and Benjamin Marchetti, that you will see at the end. I will talk about clouds. I will talk about clouds. And really, what we want to address today is the problem of particle in complex flow. And I've given a few examples. Dust storm, this is a very turbulent flow. As you can see, you have the river Rhone, which is going into the Lake Geneva, and you have all this mud which is spreading. And there is this thing which is really funny, which is this they call it sundog. Don't ask me why. And it's caused by the light scattering from hexagonal ice crystal in clouds, and you can see that you have reflection which make 3 sun. So you have 1 sun and 2 others on the side. So I don't know why they call it sundog anyway. But what really interested us in this problem is, you say, let's say you have a cluster of particles, and now how is this going to be transported? And what is interesting is that sometimes, like in Langmuir circulation here, you have particles which are collected in a particle position of the flow. And here there is this Langmuir cell which are occurring in lake, or I think in the ocean, due to the wind. And you have this Langmuir circulation. And actually you can see that you have particle, or you have, in that case, I think it could be plankton or other material, which are collected in this kind of stream here. So they kind of sort of cluster. Oppositely, and you remember some time ago that there was, but there's still some eruption right now in Iceland, but there was this pyroclastic flow of this volcano, and I won't pronounce it because I don't know how to pronounce it. You remember? Actually, I was in Kavli Institute at that time, and I think the plane in Europe were stopped because of the particles. And what I want to show you is a little recording of the particle and during that thing, and you can see that they spread at a very large distance. It was not clustering in that time, and you see that you can have transport of particle and dispersion of particle at very, very large distances. And so we wanted to address this problem in a simple way, and I know what to do. Okay, and really something which has been very important, I think, in the field, in this this thing about particle interacting with the local vortical structure in all this problem, because you have the Langmuir cell, which is vortices, and you have also the dispersion of particle, and in the atmosphere you have also vortices. And so really the idea to say what's going on when you have particle interacting with these vortices. And there has been this concept of preferential sweeping, which is the fact that if you have vortices like that, you have, due to the inertial bias, the local induced velocity field, the particle, they approach the vortices from above, and they are sweep away from the vortices like that. Okay, there had been a lot of work on that, and much more now. And we wanted to look at this this issue of how particle or a cluster of particle will interact with vortices. And really, I will have my talk in two parts. The first part, it's a sphere in a vortical flow, a single sphere, so there is no, okay. And I will describe the experiment, and also we did the experiment and also some modeling. It's a very simple modeling using Python code, which is very simple. And then I will discuss clouds. Now we will have a cluster of particle where we will have collective interaction between the particle, but also between the particle and the flow. And the idea is to see how this comes together. So I start with the sphere in vortical flow. I should use this thing. Yeah, and it doesn't work. Okay. Okay, yeah. And this is the experiment we built. And actually, we use a magnetic field, which is produced. Actually, this thing to produce vortex was done before by this in this paper by many people, but the first, I think it's the group of Tabeling, and then Vassilikos use it. And really what they wanted to look is two-dimensional turbulence. So they had, so basically what you need to do to produce the vortices is that you use the electromagnetic force. You have a fluid, which is, and you have two electrodes here on the side. And then you have a fluid which is a fluid with a little bit of salt, let's say. And then you have magnet on the bottom. And because of the electromagnetic force, you can produce current, which are really like the vortices, opposite vortices. And the big thing we did, compared to all the study that was done before, which were horizontal, we tilted the thing. Meaning that we had here our two electrodes, we have our fluid here, we have the checkerboard of magnets on the bottom, and then we drop particle with a little syringe, and then we track them falling down in this vortical field. And this is a wall. You have two walls from about 4 centimeters. The thing is like that, okay? And so on the back, you have the magnets. And then you can just drop particle with a little syringe and follow them. I'll show you the pictures.
And do they do lateral migration, and is that a problem? Is it 2D, or they go close to the wall, or they do something?
You have to drop them at a certain distance. I will show the thing. But first I want to show you the cellular flow that we get. And this is what we have. This is a PIV of our vortex compared to the Taylor-Green vortex, and you see they are very, very similar. This is for Reynolds number. K is typically the wavelength of the vortices. And so that means this is a Reynolds on the sides of the vortices, and you see it's smaller than 1. So, and this flow is interesting because in the middle you have something which is purely rotational, while on the edge here you have something which is elongational. So it's a kind of complicated flow, and you will see that the elongational part is something tricky because it's a kind of stagnation point, and that thing. Now, the thing is that if you increase the, oh, it's going too fast. Yeah, this is typically for the vortical flow. I just want to show you, which is measured by PIV for Reynolds of 0.7. So you can see in different direction. It's a quasi 2D periodic structure of size, in our case, 2 centimeters in the vertical plane. It has an endicity which reaches the maximum as 5 millimeters away from the back wall, to reply to the question, and then decay. So you need to inject your particle in a certain zone so they stay in a kind of 2D flow and are not, push away. It's tricky somehow, okay? And now the thing is that if you increase the Reynolds number of your flow.
Bottom thing?
What do you mean? Which bottom?
The bottom 3 figures are what? The top is vorticity.
No, it's just a flow field. It's just a flow field at a different position. It's different slice like that. Different slice. Yeah, you have different slice. Now, what I just want to say about if you increase the Reynolds at some point, the spatial structure change a little bit. It's a little bit distorted, as you can see. And it becomes unstable for Reynolds number larger than 15. And actually, most of the people who look at this issue, when I was mentioning Vassilikos or Tabeling groups, they were looking at the 2-dimensional turbulence and the destabilization of these vortices. But we are not interested about that. We could be interested, but you will see it's already complicated having stable vortices. And okay, so now I want to tell you a little bit about how we model that, now that I'm showing you the experiment. So it's not a big experiment, it's about that size. Huh? But anyway. We have it's interesting to make a dimensional analysis. So you have 7 independent physical quantity. Yeah? You have the viscosity of the fluid, the density of the fluid, you have the radius of the particle, the density of the particle, you have gravitational acceleration, you have the size of the vortices, and the velocity of the vortices. Basically, this is what you have. That means that if you do dimensional analysis, you end up with four-dimensionless number. And you can have additional number which are related, but there is four which are independent. You have the velocity ratio, which is the settling velocity divided by the velocity of the vortices. You have the Stokes number. You have the density ratio, which is defined like that, sort of ratio between the density of the particle and density of the fluid, more or less. And then you have the size ratio, which is Ka in the way we define it. And usually it's going to be very small, because we have particles which are much smaller than the size of the vortices, which are about 2 centimeters. Okay? And
once you fix those two, the Stokes and the density ratio,
yeah.
the W will be a derivative quantity, right? It's not an
No. You have, this is for independent number.
Oh, because you have U0.
You have U0. So you have 7 independent quantity. If you do dimensionless analysis, you end up with 4-dimensionless number.
Okay.
Then you need to choose the one you like. That's so we chose this, but there is additional number that you can define and which are derived from them. You know, there is a Reynolds number considering the size of the particle, and there is a Reynolds number considering the size of the vortices. So this is a related number which are dependent of them. So now, moving to the usual BBO equation, and which were actually derived by, we discussed that, by René Gatignol and Maxey and Riley. And actually this equation, it's for a small rigid sphere in a flow field, U, and it's really an expansion at small Reynolds number. It's important to see that. And you have different terms. This is, okay. I'm not used to this fancy thing. Oh, okay. Okay, now. You have different terms. This is just acceleration. This is the buoyancy force here, the fluid acceleration, the Stokes drag with the Austen correction. You have the added mass with the Austen correction. I put it in blue, but it's negligible in our case. Faxen, I'm sorry. Faxen. He was a student of Austen. I saved myself. Yeah. And then you have history force, and again, the Faxen correction. But actually, we don't need the Faxen thing because I told you the size of the particle is pretty small. Actually, this Faxen correction is the fact that if you have like in a Poiseuille flow, if you have a particle which is big enough, you have a correction to the effect to the size of the particle. So you have something. Anyway, so now you can use that properly. It works. I'm good at that. Maybe at the end of the talk, I will be monitoring this object. Anyway, so we made it dimensionless using the length scale, which is basically the size of the vortices, and the velocity scale of the vortices, everything. And you can see that the parameter, the 4-dimensionless parameter, which I presented before, just comes up miraculously. Okay, so you have all the different terms like that. Same different term that I have. So basically, this is drag and buoyancy. This is added mass, and this is the history force. And so now, it's interesting to look at the importance, the order of magnitude of the different terms. Okay, and the Stokes number is going to be our order or important parameter. So if I increase the Stokes number, you see that it's a Stokes number, it's very small. Inertia, history forces can be big, but still, you see you have drag and buoyancy is really dominant. And when you have a Stokes number of 0.1, you see that drag and buoyancy is still big, but inertia is increasing. History force is still what it is. And for a Stokes number of 1, probably all the terms become of the same order.
Can you explain how you came up with an order for the history term?
It's just I don't know.
Just the coefficient.
The coefficient and also the order of magnitude here. Yeah, the coefficient which are in front of it, because everything is made dimensionless. But that's a good idea. That's important, and you will see. So really the idea is to see what are the different regimes, because you can...
This will be for one particular density ratio, right?
What?
One fixed R.
Yeah.
Like if I change the R, I can change the relative magnitude.
Of course you can. Yeah. Okay. Now, if you are already in the Stokes regime, actually the first paper to look at that, it's this paper by Stomer. In the Journal of Marine Research, he was looking at the Langmuir circulation and the particle falling. And so it's just very simple. It's just drag and buoyancy. That's all. And here it's really, you say, well, the particle is falling with its Stokes velocity, and you just add the Stokes velocity to the flow field. That's not more than that. It's a very simple thing. And here are some pictures from this paper. I thought that in a talk it would be interesting to show that. And what he found, basically, in this, you had only one dimensionless quantity in that case, which is the ratio of the velocity. If it's larger than 1, the particles settle through the vortex array without being influenced. It's a kind of ballistic regime. And if it's of order 1, the particles are affected at the local flow and the trajectory of zigzagging motion around the flow. And if it's smaller than 1, the particle can be suspended in the flow. This is what he found in this paper. And
in the ocean, do you have like arrays of vortices like that?
Yeah.
And below the first Langmuir cell, there are...
I think there is a few vortices. I think there is not only one, a few, but not much, I think. I'm not. And then there was this paper by Maxey, which was a very important paper, where he looked at the BBO equation, the same equation, the neglect the history term. And so this term, everybody has neglected this term that you are interested in, because it's very difficult to compute. So the best thing is to say I neglect it. Okay, so he took everything except that, and then that's a dimensionless equation that you end up with, kind of Taylor green vortices. And this is basically what the kind of pictures from his paper, kind of figures. And the major influence of inertia is that the particle cannot be suspended in the flow, and that they are seen to settle out, even if they are trapped momentarily in a vortex. And this is what we've seen, okay, in this numerical simulation. So really, what we wanted to do is really both see what was going on with particles interacting with the vortices, but also testing this BBO equation and see what are the terms which are important in the problem. And so the first thing, so there will be, I will show you the dynamic in Stokes flow, meaning for Stokes which are less than 10 minus -2, and then the Reynolds number smaller one, 1. Reynolds for the size of the vortices. And then I will increase a little bit the inertia. And you will see that, and it will be a regime where the Stokes is smaller than 0.1, and the Reynolds can reach 6 or 8, okay? And you will see what we have and the comparison between the experiment and this BBO equation. We use water with a little bit of citric acid to adjust density. Okay, so this is typically, we inject our particle, this is the experiment, and we track them, and you can see their trajectory in the vortices. You cannot see the vortices behind it, but here it is. And this is what we get in the experiment. So you can see the vortices that we have represented behind, and this is the trajectory of the particle, the experimental particle in this, across the vortices. You can see the W is 3, the Stokes number is very small, and the Reynolds number on the size of the particle and also on the size of the vortex are small. And you have this oscillation when they settle. And we have here comparison with the Maxey model, the red solid line here. For instance, this is the trajectory and this is the velocity in the different direction. Okay? And Stommel is black dashed line that you can see here. And you see that they are identical, meaning that in that case, drag and buoyancy term are dominant in the Stokes regime. Really, the Stommel equation is enough. Okay? I need to click. Okay, now if you if W is a little bit smaller, you can see that you have more pronounced oscillation, and you have a great sensitivity to the local velocity field. In the stagnation point here, you can see that you can go in one direction or another here when you are really in the middle, because these vortices, they have, when there is the elongational part of the flow, it's extremely sensitive. If your particle is a little bit on one side or the other, it's going to go in one direction or the other. And again, if you look at the comparison with Maxey equation or with Stommel equation, it's identical. And again, drag and buoyancy are dominant, and you don't need more in this regime. What is interesting, this is what I was mentioning here, is that you can see here, this is the Maxey and the Stommel equation, and you can see that they go in the other direction, and while our particle is going in the other, because just at the stagnation point, you have a great sensitivity here. Okay.
R equal to 0.657. What is that in density ratio?
I don't know, because this is a weird, R is RF, RP, and there is RF. Yeah, I don't know. It's really.
These are like far denser, or they're nearly neutrally buoyant?
It's close to neutrally buoyant, yeah. Okay. Because that's why, yeah. That's why you change a little bit. And you can see that W is 0.8. That give you an idea. That's why we change this. We need to have an acid. We have citric acid, so we have the electric field. But also it's nice because you can change also the density. And you can change also the density of the particle, if we want. This is a sphere of 0.5 millimeter here. Now, if I get a particle which is 3 millimeter, And here you can see that this is a ballistic case where the particle is going through like that. And there is nearly no modulation, and comparison with Mach's equation are okay. There is a better agreement when I'm using the W experimental instead of the W coming from the Stokes drag, because probably the experimental drag is slightly larger than the Stokes drag in that case, because you have a particle which is very heavy. I will discuss that. Okay, so now, so in the Stokes regime, no problem. You just have drag and buoyancy. You don't need to think about anything else. It's easy to solve. Now, I want to go to a little bit of weak inertia, and this is what you have here. And here it's a sphere of 1 millimeter again, which is settling in the cellular flow field. And should I explain why? I have a question.
Hello. Hello.
I'm not sure.
Raja, can you unmute yourself and ask the question? Oh, he says there are mic issues.
Oh,
okay.
I can discuss at the end, yeah.
Yeah, we can discuss it at the end.
Okay. So here, we have increased the inertia. You can see that the Reynolds is a little bit, the Stokes has increased. It's about not 0.1, but coming, and the Reynolds number is bigger. And you can see that there is still oscillation, but there is a drift toward the border line between the cell, and the oscillation diminish, okay? And this is not due to the particle or inertia, it's due to the fact that our vortices are a little bit distorted, because the inertia, I showed you that before, and therefore the vortex are distorted. It's not completely a Taylor green vortex, a pure Taylor green. They are a little bit twisted. Okay, so if we do the simulation in the Taylor green vortices, doesn't work well. But what we did instead, we took a PIV, we injected the PIV into the little code, and that's the trick. And we found very good agreement. However, we have a drag, which is not the Stokes drag anymore. Even though we are a very small Stokes number, we have a Reynolds, which is 5. So we have nonlinear drag. So you can use some correction. The easier what we can do is the Schiller-Neumann drag, which is just a correction to the drag. And so basically what you have in that case is the particle velocity is described, really. If you look at the comparison again, you have the same comparison, but you can see that the red and the black, which are Maxey or Stoneman, are the same. But now, instead of using the Stokes drag, we're using a nonlinear drag. And in that case, it's enough. So that means that at that stage, the BBO equation doesn't work anymore, because you don't have a Stokes drag. You already have a nonlinear drag, even though the Stokes number is of order 0.1, because you have a Reynolds also, which is larger. Okay.
But this drag expression, it pretends that there's no history, there's only a local formula.
I will show you comparison. Here. Good, eh? Good timing, that's my slide. Okay, So we look at the influence of the history force, because of course, okay. And here, typically, this is x2 is along the direction, and this is x1 is, so you have the oscillation here. So this is, okay, so you have the Stommel model, which is just drag and buoyancy with a Stokes drag, which is the black dashed line, okay? The full Boussinesq-Basset-Haussine model in the Stokes regime, which is the blue line, and which is here, and then you have here the experimental, and here you have the experimental here, and you have the Stommel model corrected with the nonlinear drag, which is in red. So you see that even the full BBO doesn't capture because it has a Stokes drag. And what you really need is the nonlinear drag.
Yeah, I mean, at the high Reynolds, you would expect that at 5 or whatever. But like this formula is local in time, right? The nonlinear drag, the Schiller-Neumann.
Yeah.
It's kind of local in time. Like I would have thought there'll be a history, maybe not like the BBO term, but some history term.
What I see here is that taking nonlinear drag and buoyancy, you can see that it's doing a good job in capturing the experiment. Now, if you have just the BBO with the Stokes drag, it's in blue, and you see that you do not capture the oscillation properly. Okay. Now, maybe in a different vortex, if you have a very, what I think is that the history force is really important when you have fast motion, fast also acceleration, which we don't have here. So basically what I want to tell you here is that our system, as soon as we get a little bit of inertia, the BBO equation is not working, and you need nonlinear drag. And you know, the inertia is not big. Huh? It's Stokes number of 0.1. Now, I want to show you a little bit more here. And you will see here, you're going to like this one because it's close to neutrally buoyant, but it's still settling, and it can be trapped momentarily into a vortex, as you can see. It can turn for several times, as you can see, and then it eventually settles down. And of course, there is a great sensitivity to the initial position here, on when you arrive at a certain, here at a saddle point. But still, we try to reproduce this with the just drag and buoyancy, nonlinear drag and buoyancy, and this is what you see here. And it works not so badly. Okay. Okay. I need to click here. So basically, the conclusion of that part is that it's nice to see the motion of the particle around the vortices, but we also tested the BBO equation. And really, what was surprising is that even for a Stokes of 0.1, the nonlinear, you need the nonlinear drag. That's what it is. Okay. Now, I want to move to something more complexity, and to say now, instead of having one particle, I'm going to have the interaction between a few particles, a cluster. Now, a cluster, and the question will be to say, if I have a cluster falling into vortices, does the cluster stay really an entity, or does it disintegrate completely? Okay, that's the question. And it is the fact that do the vortices lead to more disintegration of the vortices or not? But first, before going through that, I want to talk about clouds settling in quiescent fluids, because we need to know what's going on first without going to vortices. And this is what I want to talk first. Okay, and first I want to talk of vortice of cloud settling in the Stokes regime. And this is actually, this work was started by Batchelor. Actually, this is the last paper of George Batchelor. Yeah. And there was a few other work, and we did some work here. We did some experiment here. And this is experiment here and Stokelet simulation. And basically what you see when you start with a cloud like that, the cloud first have an internal toroidal circulation like that. Actually, it's similar to what you have in if you have a sphere of different fluid falling, yeah, which is giving you this toroidal circulation. This was calculated first by Adamar in the early 20th century, and you first had that, and then the cloud remained roughly spherical at first, and then there is a leakage of particle behind the cloud, and there is a tail, and then it evolves into a torus. You cannot see it, but I will show you. And then eventually the torus spread and break into two droplets in a repeating cascade. And this is in Stokes flow. Okay, there is no inertia, nothing. And here it's a simulation. I will tell you what it is. It's Stokelet simulation. Stokelet, it's just, I will explain what it is, but it's strictly the Reynolds number is 0. So you can.
It always breaks into 2.
Yeah, exactly.
Whereas the ink drop does not. It breaks into 7 or 8.
Yeah, yeah. Well, drops, you need inertia for them to break. That's a different, that's why. I will, here it's without any inertia, okay? And the important thing in this problem is the fact what's going on. It's that at the beginning you have a cloud and you have this toroidal, this is the flow field around the cloud, given in the Stokes regime, and you see that you have this toroidal circulation. And actually, if you think about the particle here, this particle has a chaotic motion because it receives the interaction from the other particle, the little perturbation. So it's, and basically it's going here. And you see that the particle which are at the rim of this toroidal circulation can eventually escape from the cloud in a tail like that. And that means that you have a depletion in the middle of the particle, meaning that they form the cloud becomes a torus, and then it expands and then it breaks. It's a little bit more complicated. We've studied that. I'm not going to talk too much about that because that's not the point, but this is what I want to tell. And here it's, you can do a numerical simulation of this. You can see very easily. This is done in Python. And basically what you have, it's a minimal description. It's a point particle. And the idea is when you have a sphere falling in a fluid at Stokes regime, you know that the perturbation, velocity perturbation due to the disturbance due to this particle is going like 1 over the distance to the center of the sphere. So basically what you do is you say, well, if I have one particle like that, this particle is settling with its Stokes velocity, and then I had the different disturbance coming, which are going like 1 over r, coming from the other particle. This is what this Stocklet is, and then this is what you have. I can show you the movie again if you like it. Okay, you have first the circulation, you see the tail, and then it expands, it breaks. And we can see exactly the same thing in the experiment.
So if you have a very high number density, then the escape will be easier, right?
Well, yeah, they will escape. Yeah.
They will be affected more. And
Yeah.
So then there should be a time rate which is
Yeah,
connected to the
actually, you need a certain number of particles for
this thing to settle.
For the thing to become a torus. If you have a small number of particles, you just have the tail and then the cloud dissolved like that. Otherwise, if you want really to have a torus and the expansion of the torus, the two little droplet, you need to have a large number of particles. It's really what we did in this paper at that time. We really compare carefully experiment and this very, very simple numerical simulation, which was coming from this paper from Bachelor and Nietzsche, the last paper of George Bachelor. Yes. Yeah. Actually, it's a number. It's really the number of particles which tell you. Yeah. I can show. Yeah. I'm sorry, I didn't understand.
The breakup of the original cloud, like, does it depend a lot on what the value of VS you select? Because I think, is that something which you choose as a parameter, or is it something which comes in?
I think I've not.
The VS, the first term on the right-hand side.
Here?
Yes.
Yeah.
No, the one before that.
This?
The settling velocity.
It's the Stokes velocity.
Yeah, the Stokes velocity.
Yeah.
So that's something that you prescribe, correct? Is that something that you put into the problem?
Yes, but it's just the velocity of the particle in this regime. It's just the settling velocity of the particle.
I'm just asking if the breakup has got some dependence on this.
No. The breakup has the time of when it's breaking up. It really depends just on the number of particles.
Thank you.
Yeah, I can discuss more than, but I didn't want to say too much. I just wanted to tell you what's going on when you don't have a vortex. Okay, and so need to. So now, if I have a little bit more of inertia, things look the same, they are different. So this is the experiment, and this is the numerical simulation. And basically what happened is that you can see that you have this drop, it forms a torus again, and then it widen and break. But you can see that there is no leakage at all. And then no leakage. And actually, what happened and what is important here, it's the wake behind. Because what happened now, if you have a little bit of inertia, is that instead of being in the Stokes regime, where you have, when the particle in Stokes is falling down, it's perfectly reversible. So you have the streamline, which are perfectly identical from one side to the other, while where we have a little bit of inertia, you have the Aucine wake. So you have an Aucine wake behind the particle, which is attractive. You know this problem because you may have seen this thing which is called drifting, drafting, kissing, where you have two particles like that, where they are attracted. There's This is normal. So when people are cycling, because they go behind, so they are carried by the first bicycle. So you have a particle which is attracted like that, and it's kissing, it's tumbling, and it's expelled. So what the flow field, there's no more the symmetry that you see in the Stokes regime, and actually you have an attractive wake, which is attractive with a flow field which is going like 1 over the distance, and in front you have something which is repulsive going like 1 over r squared. Okay, so basically you have wake, and what happened is that instead you have this recirculation like that, and instead of going out, the particle cannot go out because you have this kind of big wake, and the torus flatten and break.
So this simulation is steady oscillate?
Yeah.
So you're neglecting acceleration?
Yeah, we neglect acceleration. I know that you have also acceleration and everything, but strangely, you will see, it works very well. I know I've discussed that with John Lynch a lot, because there was a lot of discussion, because you should not be really in this steady regime, but if you use a wake, it works. And what I want to, do we see increase in wake interaction? I don't know. I don't know. Yeah, probably yes. Yeah.
So he's asking, is there a limit to increasing the
particles? Yeah. This I don't know. We have increased the number of particles, but we did. I don't think we did it systematically, but yeah, they should do that. And basically, I want to show you what we have with the oscillate. I will redo the thing. First, I will show the oscillate is a little bit more complicated. And of course, you have an additional parameter, which is the inertial length, which is the size of the particle divided by the Reynolds with the size of the particle, which is the oscillate length. Okay, so this is a flow field, a stationary flow field. And again, it's a simple. Nice thing is that it's irreversible, but it's still linear, weirdly. So you can add things. Again, that means you have a particle, and the Stokes velocity is still the same in the oscillate regime. I mean, the particle is falling with a Stokes velocity, and then you can just add the interaction, and instead of being the Stokelet, it's just the oscillate. Okay, and I will show you again this numerical simulation. You can see the torus breaking, and it's not only 2 drops, it's a few drops. Okay, and this was really inspired by this numerical simulation, and the comparison, the experiment what we did was really inspired by this paper by Subramanian and Koch. Okay, just to tell you what's going on when you have a quiescent fluid. Now, I will have my little cluster of particles falling into the same vortices, and I want to show you that. I need to press here. Okay. Here. And this is the same system, and we can track the trajectory of the center of mass of the clouds. So we have that. It's the same, exactly the same system. It was a little bit more complicated. We had 2 cameras to track them very quickly, but that's not a thing. And basically, the color is the distance from the wall. You can see, which is here. Okay. And basically, if we want to model things, we took the thing which is the simplest possible. There must be more complicated things, but anyway, things what we can do with Python. you know, for experimentalists. So we have a dimensionless equation again, and we take this point particle approach again, and we take the Stommel model somehow. We have just buoyancy and drag, but now we add the different contribution for the other particle. If we are in the Stokes regime, it's going to be the Stokelet. If we are in an inertial regime, it's going to be the Ausenlet. It's a very simplest thing we can do. I'm not saying that it's perfect, but the idea is to say what are the minimal ingredients which can reproduce what we have in the experiment. And here is what we have in the Stokes regime. This is the experiment on one side. This is the Stokelet simulation on the other. You can see the zigzagging motion, which are again due to the cloud is stretched in the elongational region of the flow. You can see that. And you have some leakage. You can see. We cannot see that in the experiment that they exist. And
is the velocity field experimentally obtained or described?
Here it's in Stokes regime, so it's good. Yeah, it's an analytic expression. So, and you can see that actually you don't have any breakup here, and because the travel distance of the cloud is not long enough, and the clouds need to fall at least 500 times reduced to the breakup to occur in that case. It depends on the number of particles, but we have a lot of particles here, but still. And we have similar qualitative evolution of the experiment and the Stokelet simulation. This is a Stokes regime, so. And I want to show you more precisely, more quantitatively, what we have. So this is the time evolution of the vertical and the horizontal coordinate of the cloud, of the center of mass. And then we have the vertical velocity and the cloud projected surface, because we want to see what's going on when if it's increasing or not, you know, when it's stretching like that. And you can see that well, the mean settling velocity is similar to what observed when falling in a quiescent fluid. It's not very different. But you can see that you have this oscillation because the clouds slow down when it's and expand. You can see here and expand when it's going through the different upward and downward motion of the vortices. You can see that there is this oscillation, and we took different simulation because it's very difficult to know exactly where is the center of mass of the cloud. So we did a sort of error bar by putting thing, and we did some different position to see, and you can see that it's not so badly represented in this regime. Now I want to show you now when I increase inertia again. It's the same idea. And when I increase inertia, this is what happened. The experiment on the left, the Ausenlet simulation, you can see that at some point, the cloud expand and break. Okay? You have really a stronger deformation by the flow structure, you've seen, huh? And the simulation, it's the simplest thing. It's just having a wake. I discussed with Fabien Candelier, and I told me, we discussed, I said, it's weird because somehow it's just the Ausen stationary Ausen wake, and it seemed that just having a wake does the job. Does the job. Strange. More quantitatively, it's the same quantitative thing. You can see that the trajectory cannot be followed for too long because it breaks up. But anyway, so the vertical position, it's follow approximatively straight trajectory, and the horizontal position and the velocity, they present oscillation. What is interesting with the velocity is that there is a double period, you see, a sort of double period what we see. Probably it's a successive slowdown and acceleration during the fall, but that's it's a new feature that you have when you increase inertia. And and now we want to understand a little bit more what's going on with this thing. And here it's just numerical. We cannot do it in experiment. So this is on top is the Stokes regime. Here the finite inertia regime. You have the original PIV. We took the PIV, actually, it's easier. We took the PIV, as we said, and we inject into the simulation, because in the inertial regime, the vortices are a little bit distorted. Okay, and in blue, it's the flow line which are distorted by the cloud. So you can see that there is a strong impact, the kind of two-way coupling. It says two-way coupling of the cloud on the thing. And you can see that here, when it's going to you have the oscillation, of course, but you have expansion and contraction of the cloud when it's settling in the successive upward and downward portion of the flow. When it's downward, it's stretching like that. When it's upward, it's stretching like that. You can see that there is a difference, is that it's very enhanced in the oscillate case.
So how did you do the two-way coupling?
It's just the oscillate. It's the fact that you add.
So you just put it back in the fluid equation?
No. The fact that it's exactly the same thing, because we have our stationary flow, but since we take into account the interaction between the particle, so you're doing this. I know that causes perturbation to people who are used to do a two-way coupling and things like that, but that's a simple two-way coupling for people who can just use this. Anyway. So the important thing here is really that the deformation of the cloud is really important when you are in the inertial case. And here it's an idea of the physical picture of the mechanism leading to the breakup. Here it's a flow field, and in the cloud reference frame. And when you have inertia, finite inertia, the oscillation between the expansion and contraction phase are not reversible anymore, and the cloud expands more. So it expands more and more, and at some point it breaks up. So basically, the vortical structure induces a faster breakup in the case of inertia, because of the fact that the expansion and contraction are not no more reversible. Okay. Now I wanted just to show something which is very simple, because people ask me the question all the time and said, what are the collective effects doing? Because the vortical structure are inducing the breaking, but what are and here I've done very simple numerical simulation with you increase the size of the initial cloud. So here you can see that the initial cloud is small compared to the size of the vortices. Here is larger, or the same order. And also here it's with the collective effect, I mean the interaction between the particle. Here it's without the collective effect. I switch off, okay? Here it's with the collective effect, with 500 particles. And now I increase the number of particles. And again, with collective effect, without collective effect. So I'll show you what's going on. And you can see that, of course, without the collective effect, I mean, the particles are just trapped in the upper vortices. And what is interesting is that if you have a lot of particles and that the collective effects are very strong, this maintains the cloud as a single entity for a long time. I can show you this again. You can, here, you can see that in that case, it stays a single entity for a long time because the collective effect are sort of maintaining the cloud. Okay, just to give an idea, because okay, it's time to stop now and to say my conclusion. And really, we wanted to do here, it's really a close examination, comparison between experiment and the simplest model that you can think of. And I think we tested this BBO equation. And I think the main message is to say that as soon as you have a little bit of inertia, you have a nonlinear drag. And this becomes the dominant thing. And I don't know for the Bassett term, the history, but the
BBO is not meant for that case, right?
It looks like. So we need...
meant like it's only for a zero Reynolds.
Exactly, or for something extremely small. That's why. And also there have been a lot of numerical work where people are using the BBO equation with large Reynolds number, of large Stokes number, and we can doubt. I mean, this is, you can do it numerically. But you can see that experimentally, as soon as your Stokes number is 0.01, you have nonlinear drag. Okay, so I think point particle are interesting, or this simple model are interesting because you can see really what are the physical mechanisms which are behind. And I think this is the idea we have. And really, the collective effect is interesting because it's help maintaining the cohesion of the particle. And I think it's important to have that if you want to model when you have a cluster of particles, we have many particles and that the density is increased. I think you need to take into account the collective effect. And we have identified this mechanism of expansion and contraction of the cloud, which seems to be important to lead to disintegration of the cloud in vortices. So this is what I wanted to tell you. Thank you. And I can maybe reply to the question or more question. Oh, doesn't work. Doesn't. Okay. Ah. Oh, I don't hear anything. It doesn't work. Oh, there's another one. Look.
Hello.
Yeah.
Okay, great.
Good.
Yeah, thanks for the talk. It was very interesting to see all the experiments. In the last part, you were saying how if the cloud is large enough, then it maintains its maintains itself as a single entity. But actually, the size is increasing.
Yeah,
right?
of course. You need to have a big size also. Yeah.
So this may go to like explain the kind of things that you showed in your earlier this thing where things kind of spread out, but they seem to be a single entity. Like I don't quite remember what that phenomena was, but something that originated in the
the Osino or the disintegration. You need to have
no. In the earlier, she was showing some real life examples of
real life example.
So I was wondering
Like,
if there was a connect that you could make with this particular the observation.
Yeah, I don't know exactly when in natural flow it's always complicated because there are vortices and things, but yeah, I think collective effect have a tendency to maintain the cloud as an entity. If you have a cluster of particles, it will be maintained more.
But will the size keep increasing over a period of time? Or?
No. You see,
Okay.
it's seems to. It will disintegrate eventually, but
Okay.
it will take more time, I will say.
Hi, thank you for the nice talk. So I have a couple of questions about the simulations of cloud of particles. So in your case, the interactions go like 1 by r, where r
Yeah.
would be the distance between the particles.
In the Soclate case, in the ocean net, it's a little bit more complicated.
Yeah. Do you find any cases in which you have r going to 0 in your simulations, where the particles would be coming very
You
close?
have a problem in at the center of
the distance between the particles going to 0.
But it doesn't cause most problem if you have enough particles.
I'm asking, let's say for 2 particles, if you have for 2 particles, any 2
for
particles.
2 particles, there will be a problem. Like if you take 3 particles like that, let's say you take 3 particles. This one in the middle will fall faster. The other will go like that and they collide. That's going to be a problem. But if you have many, it's not a big problem.
I'm talking about among the cloud of particles. If you let's say take 2 particles, any 2 particles, do you see that the distance can go to 0 in your simulation? Do you see that happens?
No.
They don't come too close to each other. So you don't have to worry about the divergence.
There's no. In the simulation.
Simulation.
No, in the experiment, of course, there are entity. No, in the simulation, it's not a problem.
If you increase the number density, it may.
If you have a few, very few particles, that might cause a problem. If you have enough, there's enough perturbation and disturbance that it doesn't happen.
I see.
It's very easy simulation. I think I gave the code in the papers. I think as supplementary material, or I can give it to you. We did it first in MATLAB and then in Python. It's very easy.
And also,
I'm not an expert in simulation. I'm using just the.
And also, do you switch between Oseen-led interactions and Stokes-leds when the distance between the particles come closer than the inertial range?
No.
Do you think it would be more accurate to do it because Oseen-led is far when they are farther than the inertial and scale?
No, actually, here in the case where we use Oseen-led, I mean that means that the wake between the particles are interacting, so they are pretty close.
They're pretty close.
Yeah. So that means that we need to have interaction between the wakes. And using Oseen-led, even though it's not perfect and correct in the sense that it's a steady Oseen-led, it's giving you a wake, and it seems that having a wake is enough to explain some of the phenomena.
I see. Okay, thank you.
Hello. Thank you for the talk. In the last part, you showed that if there is no collective interaction between the particles, a lot of the particles get trapped in the vortex of the top layer. And even there is an intuition that weak inertial particles mostly behaves like tracers. So in the first part of your talk, why were all the particles falling through? They were at low Stokes number.
But here the particles are much smaller.
Okay.
Much smaller, and I think the density is not very high.
I see.
I mean, the ratio of density is not very high. It will depend on the ratio of density. Of course, if you have a very, very dense cluster, if you switch the the aerodynamic interaction, your particle may fall, you know.
All right, thanks.
It depends. What you have to see is that I put parameters in the simulation which are realistic. Because I see sometimes in numerical simulation, people who will use a Reynolds, which is 0, and a Stokes number of 100. If you can make a particle in real life like that, let me know. Because I have no idea.
Questions?
There is one.
I have a bit of a naive question. So you are near neutrally buoyant particles in the first observation, and then but still they were heavier than the background flow. So what was causing them to get trapped inside the cells? Like if you have a small enough particle, it will just gyrate outwards.
If they can get trapped into
He
the.
said, what was the reason they were getting trapped? Because they're heavier than the fluid, so they should leave the vortex.
Oh, yeah. But they eventually leave the vortex. You mean they can turn in a vortex if they are light enough, and then eventually settle.
Right, but so initially they were like tracing these boxes outline, right, of the Taylor-Green vortices, and then they were coming inside. In one of the slides, you showed that.
Yeah, but then eventually they fall.
Eventually, but like, what was bringing them inside the vortices?
They fall into the vortices, and then they carry up.
Because gravity is.
And gravity.
And then they're spiraling out.
Yeah, you have so the particle fall because of gravity, and then if it's not too heavy, you have a balance between buoyancy and because you have just in this case the settling velocity and the velocity of the vortices. So the vortices depends if the particle is falling and then it catch up in a vortex and the velocity is higher, it can be trapped.
Okay.
Yeah, excuse me.
Okay.
Yeah, thank you for the talk. I just have a very brief question. Like, are there any atmospheric flows where you see these kind of, what is the relevance of this in atmospheric flows, for example?
In atmospheric
flows, what is the relevance?
This is a very model experiment. So I don't know, in atmospheric flow.
Like aerosols and all can be thought of as like a cloud of aerosols falling, and can those.
I think if you think about aerosol or thing like that, you will have, my feeling is that the relevance is that my feeling is that you will need to have a nonlinear drag and buoyancy, and maybe a little bit of, if they are very heavy, maybe a little bit of added mass, but that's all. Maybe
there are two questions there.
Okay.
Why is the wavelength twice of the vortex structure?
Where is it?
Basically, it goes through two vortices for one wave.
Yeah. This?
Yeah.
Oh, yeah. Because
he's saying, why is it twice? So you could tell.
Oh, the little thing, which one is it? On what page? Page 22. Okay. I have to look at page 22. Where is it?
And I think the next question you answered during the talk, but it's on page 22.
It's on page 22. Okay. Where is my page 22? Let me see. I'm going to look. This? Yeah. This one. Oh, the one in the middle? It depends where it falls. Huh? Really? Because in the middle, if you are in the middle here, let's say you are in the middle, what you see is the upward flow and the downward flow. So you may not go down. I mean, you just go down. But of course, there's little perturbation, and you can have a little oscillation here. Okay. But I don't think it depends the position inside the vortex structure where you're falling. Yeah.
Sorry. Given that you're in slide, I would like to press my question. Like the Stokes number you're using is order of 10 to the power -4. Still, we don't see any kind of trapping inside the vortices.
Yeah.
Like the particle does not spend a one entire loop in the vortex. Why is that? Because
you have gravity. In that case, depends a little bit.
Even at this small Stokes number, because
but depend on W.
I see.
You will need to have something which is smaller.
Right.
Well, if you
Sorry, I don't
if you have a particle which is neutrally buoyant, it will turn forever.
Right. And R is almost close, like R is close to neutrally buoyant particle.
Yeah.
So I'm a bit confused why it's not circulating in a vortex at least once.
You think it should stay in the vortex?
At least for some time before, like you said, centrifuge out and then fall down.
It won't.
Like,
you expect what? I think I am not understood.
So there are vortices and it's a small Stokes particle. So it should behave like tracer, except it should drift downwards. That's my expectation. So
but it's heavy enough to fall down.
But the Stokes number, I guess I'm thinking of Stokes number as a representation of size and R as a representation of density ratio. In that case, Stokes number and R both are small enough so the particle is slightly buoyant and very small.
Yeah.
In that case, shouldn't the particle trace out the fluid mostly with some small
But
drift?
it has some...
So you can imagine that if I shut off the vortices, it's going to fall.
Yeah.
Now, if you switch on the vortices, but you have a fluid number in your hand, that was one of the non-dimensional numbers she showed.
Right.
So if your U of the vortices is small compared to gravity, it will fall. Doesn't matter what it Stokes. No?
I see.
Yeah.
Okay. Okay.
It's a W, I think, which is
Right.
important.
She has another parameter in her hand.
So that W increased in the last simulation when
I think in this kind of in Stokes, it's W, which is the dominant parameter.
So in the last video that you showed where particles were getting trapped, the W was larger, much larger than this.
Which one?
In the last collective behavior.
Okay.
Where the particles were trapped.
Okay. Let's see. This?
Yeah.
This is simple numerical simulation.
Here we see W is 0.1 where the last one was 0.8.
Yeah, but okay, here W is on the size of the particle, on the small particle, not the cluster. That's why also to reply to one of the questions, they stay trapped in the vortices above. That's reply also to your question. It really depends on the W. And here the W, you see, it's 0.1, and which is pretty small, meaning that the particles are small enough to be trapped, as you can see. Now, when there is a collective interaction between the particle, the hydrodynamic interaction, you see the thing is different because the cluster maintains its entity for a longer time. Yeah.
Thank you.
Any other questions? Okay, it was a really interesting lecture.
Thank you.
Thanks so much.
Thank you
Madhava.
so much.